Thanks for coming out. I'm definitely very excited to be here. I've wanted to give a talk here for quite a while. So my name is Sunny Beatteay. I also go by Sunny. And the topic tonight is guaranteeing consensus in distributed systems with CRDTs. And so if you aren't familiar with CRDTs, it stands for conflict-free replicated data type. And if you aren't familiar with that, then you're in the right place, because that's what we're talking about tonight. Hopefully you got the chance to look at the paper tonight. I don't blame you if you didn't, because it's 22 pages, so not all of us have time to read through that. But after this talk, if you want to look at it more, here's the Bitly link for it, 2011 CRDT paper. I'm not sure how many of you were here 2 months ago, but there was a talk by an engineer at Pivotal. I believe his name was John Feminella. He gave a talk on the impossibility of consensus or distributed consensus. So I thought this would be a cool follow-up to that, because the paper he presented was published in, I think, the early 80s. And definitely a very good talk, but there's also been a lot of developments in distributed systems since the 80s. So I just want to give a more recent development, which has been CRDTs. So a little bit more about me. I'm an engineer at DigitalOcean. And so part of the reason I'm giving this talk tonight is because I'm an engineer at DigitalOcean. And we work on a variety of distributed systems. I work on problems involving multiple sources of truth, all the kind of issues like that. And so while I don't work with CRDTs at my current role, I've just been exposed to a lot of issues and the problems involved with them. So I've been researching them, kind of the different approaches to tackle them. And CRDTs have come up. And so for the past year or so, I've been kind of looking at CRDTs, playing around with them a little bit. But one thing I've noticed is not a lot of other engineers quite know what CRDTs are. And so by raise of hands, who here is very familiar with CRDTs, maybe has worked with them personally? Cool. And then who here is not at all familiar or maybe has vaguely heard of them? Awesome. One reason I think that's the reason, or one reason I think that not a lot of engineers have heard of them is because the information that's accessible is not very accessible. It's very dense language, very complicated proofs. This is an actual excerpt from the paper that I'm talking about tonight. And I don't know about you guys, I took an intro to discrete math in college. I don't understand any of this, but I'm sure the people in the audience who do. So if you do, please come talk to me after this, because please explain that. So the other reason why I'm giving a presentation on CRDTs is because I want to explain them in kind of as simple terms as possible, because I want to make them much more accessible to kind of your general audience. Because I think there's actually a lot of potential with CRDTs. They're a very, very cool idea. They're still pretty new, and so I think there could be a lot more research and a lot more things done with them if there's more kind of information out there. So before we get into the actual meat of CRDTs, I kind of want to give some just general history of kind of why they've come about, what problems they actually tackle, and so yeah, let's get into that. So as many of us know, consensus in distributed systems has been a research topic for many years, actually many decades. Pretty much as soon as engineers figured out they can run the same application on multiple machines, consensus has been an issue. So imagine all of us, maybe 80 of us, imagine we're all trying to build an app, such as like a Google Docs type application. Our system might look something like this, where we have multiple users trying to collaborate on a common document, on a common state. And so we might have different users submitting changes to the document, but those changes might go to different nodes in our system. And so the nodes in our system have to communicate with one another to maintain the consensus in the state. And so when we're building this type of application, there's a lot of optimizations, but also trade-offs we have to kind of worry about. And kind of the most well-known trade-off is the Cap Theorem. So you got consistency, availability, partition tolerance. Pick two of them. That's kind of how the theory goes. And so for a lot of distributed systems, the main optimizations that are chosen are availability and partition tolerance, and consistency is typically the trade-off, which kind of leads us to something called Eventual Consistency. So you can read this comic while I'm talking. So it makes sense for a lot of applications, though, because imagine you're Amazon. You want to have a highly available system where users can always write data, because if you can't write items to your shopping cart, your users can't shop. Same kind of goes for partition tolerance. If one of the data centers that you're using gets struck by lightning and your app goes down, users also can't buy things. So you're losing money in this case. So they opt for a more eventual consistent system, which in this case means that the states of your nodes in your system can diverge temporarily before eventually coming back into consensus. So that's kind of the definition that we'll use here. But eventual consistency runs into a lot of issues, especially when we talk about things like network partitions. So imagine that we're building Google Docs, it goes live, and users are using it. And so we have this scenario where two users are using our document, or are using our application, they're collaborating on a document, but then one user gets cut off. So we have kind of a subsystem that's getting cut off. And the user might not even realize they're cut off. So they keep just typing away at the document. They keep adding characters to the document. So their state diverges a lot from the state of the rest of the system. And so once that partition is kind of overcome and the system comes back together, we might have a huge imbalance that we have to get over with. We have to get a consensus with. So it might look something like this, where before the partition, both users just had a hello. But then during the partition, when one user is cut off, one user writes hello world, other user writes hello smiley face. So once the partition comes back together, or like there's no more partition, and the state is connected, we have a divergence here. So how can we actually get the state back into consensus? What kind of different possible consensus algorithms can we look at? And so there are a different variety of consensus protocols we can look at. One that I'm sure we're all very familiar with is kind of the Git style, where you have a manual override. So whenever the conflict is detected, essentially Git just tells us, hey, conflict's here. You figure it out, tell me what it is, and then I'll make it official. So we could do something like this, where whenever there's a conflict in our app, we just stop it, tell the users, hey, you guys figure out what the difference is or what the solution is, and then tell me. But in that case, our app probably won't be the most user-friendly, just because we're constantly stopping and telling the users, hey, there's a divergence or there's a conflict. So we're probably not going to choose this style, just because it's not going to be very user-friendly and no one will want to use it. Another solution we could pick is we could just take one of the states, make that our main state, and just get rid of any other diverging state there is. So this is kind of the blockchain style of doing things, because in blockchain, you don't want to have duplicate transactions. So you're going to pick one chain to be your state, and then any other side chains that develop off of it, you're just going to prune off. So we could do this, where if there is a conflict, you just pick one of them randomly, and then say that's it. We're going to get rid of all the other diverging states. But then again, this is also might not make our app the most user-friendly, because imagine you're typing along, and then all of a sudden, your entire document gets wiped out and replaced with something else. No one's going to want to use that application either. So ideally, what we're looking for is some sort of algorithm that can merge the conflicts together based on the user's intention. So what I mean by that is that whenever a user is making changes to our system, they have an intention behind it. They want to change something, or they want to save some sort of state. So if we could have some sort of algorithm that can detect the different intentions in mind and just converge them together as best as possible, that would be the ideal solution. So in this case, if we had hello world and hello smiley face, we could just have, oh, why not hello world smiley face? Comes together. So there are a variety of consensus protocols that allow us to do this. The main one for a long time has been operational transformation. So since like the early 90s, that's been the de facto go-to. And so a lot of applications are built on OT. So you got Google Docs, Dropbox Paper, a variety of other things are built on OT just because it's been a de facto for so long. But OT is pretty complicated to use, because the way it works is essentially your system has to be knowledgeable of all the concurrent edits happening at once. And it has to know, okay, these two edits might conflict with these three over here, and so we're going to transform these two to work seamlessly. So we're going to transform any conflicting edits. And you might imagine that there's a lot of edge cases that come with that, just having to know all of your concurrent things that are happening in the system. And so even though OT has been researched for a long time, a lot of the solutions have just been wrong. So you can see from this graphic, all the X's, those are papers that have been published kind of proposing a possible OT algorithm that just either was unreliable, didn't cover all the edge cases, just didn't work. Now there are some that did work, but a lot of them require central server architecture. And it kind of makes sense, because if we need to be knowledgeable of all the concurrent edits happening in our system, the easiest way to do that is to have a central point where all the edits kind of go through. So we have a central authority dictating how the edits will get merged together. And that's totally fine. You know, a lot of applications work this way, but it's not the most ideal solution for everything. You know, imagine I have my phone right here, my laptop's about a foot away. If I wanted to merge data or I want to sync the state between my phone and my computer, ideally they could just talk to one another. But in a central server architecture, my phone would need to talk to my computer through a central server potentially halfway around the world. And so it could work, but not the most ideal solution. So that's kind of where OT breaks down a bit, is how can we get this sort of consensus but in a decentralized manner? How can we get around this central server architecture? And there have been papers that do propose kind of a decentralized OT, but they're really complicated. So that's kind of where CRDTs have come in, because researchers wanted to address a lot of the issues that come with OT when you talk about a decentralized or a peer-to-peer system. And so, as I mentioned before, CRDTs are a very new discovery, or not discovery, but a new research topic. You know, here it says the topic, or it's been researched since around 2006. The paper that I'm talking about tonight, that I'm referencing, wasn't published until 2011, and it's been kind of the main paper. After this paper was published, a lot more research has been gone into CRDTs. So it's probably less than, like, the majority of research is less than a decade old. So now that I've talked about the history, it kind of makes sense to ask, you know, what are CRDTs now? Let's define this term, conflict-free replicated data type. Yeah, so let's get into it. The easiest way to do it is to kind of define it backwards, if that makes sense. So I'm gonna go with DT first, so data type. In a simple way, it's just an object that stores and models data. The thing with CRDTs, though, is that, actually the kind of great thing about them is that any data structure can be a CRDT. Because a CRDT itself is not really a thing. It's more of a concept. It's a design pattern. It's a way to design your data stores to work in a decentralized manner. So you can't say that a CRDT is an array or a CRDT is a hash table. It can be kind of, any data structure can be like it. It's similar to REST in that way, because REST itself is a concept. You can implement REST using XML, HTTP, and JSON, but it's not a thing itself. It's more of a concept. So that's kind of the way, same with CRDTs. Next is replicated. So CRDTs are kind of designed with decentralization in mind, because if you have a cluster of CRDT nodes, each node has a replica of the CRDT on that node. And so they are all a replica of the same state, so they're all maintaining, they're trying to maintain that same consensus state. And they do this through asynchronous communication. So whenever one CRDT node receives an update from a user or a client, they will first update their local state, and then asynchronously communicate, like broadcast out that change to the rest of the CRDTs in the system, so they can also update their state and come to consensus. So they do a lot through asynchronous communication. So the last letter is kind of the crux of the entire thing, so conflict-free. So this is where a lot of CRDTs, like this is kind of the fame of it, is that CRDTs are designed that all updates to our CRDT, to our data store, merge without conflict. So this is a kind of a big change from OT, because in OT, there were conflicts, but you had some sort of authority that dictated how they merged together and was knowledgeable of how they could merge together. In this case, our CRDT is designed so there aren't any conflicts. There aren't any merge conflicts. I know that could be a little confusing. We'll get into it definitely a little more. But this fact that you can, if I give you a CRDT node and you can blast as many updates as you want at it, even concurrently, and all those changes will come into consensus without issue, allows us to do a lot of things. Because now we don't need that central authority to tell us how to merge conflicts. Each CRDT itself is its own authority. So that's nice, because if we have a system full of CRDT nodes, they will communicate to update each other with the new updates in the system, but they don't need to communicate to say, hey, what's the new current state? They will already know because they've received the updates. So that allows us to have more of a decentralized system. And also another thing is that it allows us to tolerate a lot of partition loss. Because say we have a distributed system with a bunch of CRDTs, if half of it gets cut off, the half that's still working or is still operational, since they're all their own authority, the paper says that you can lose up to n-1 nodes and still work. So essentially, as long as you have one CRDT node working, your application will still keep working. So that's kind of the idea behind it. So it allows us a lot of tolerance to losses. Now, while it can work with just one CRDT, ideally you have multiple. And so they need to communicate to each other in some manner. So there's kind of two big ways that CRDTs communicate with one another. There's state-based CRDTs. So what this is whenever a CRDT node receives an update from a client. So in this case, a client is, so CRDTs will communicate with one another, but whenever I mention that a CRDT receives an update from a client, it means more of a user. So like if we're building Google Docs, our client are going to be our users. The client is never going to be another CRDT node, just kind of a descriptor or definition. So whenever a CRDT receives an update from a client, like a new change to our state, it will apply the change locally and update state, and then it will actually submit or broadcast out its new state, so the entire state to the system. So an example of that is, say we have two nodes. They both are in consensus right now with a state of 4. So their state is just a counter, just a number. But node 1 receives an update from a client saying, OK, increment the counter by 1. So node will update its state to 5 and then just broadcast out the new state to the rest of the system, in this case just node 2. Node 2 is going to receive the new state and then update to 5. So in this case, they've communicated through state-based communication. The contrast to that is operation-based CRDTs. And operation-based, it's similar in that whenever a node receives an update from a client, it's going to update its local state. But instead of submitting or broadcasting out its new state, it's just going to pass along the operation that it itself received. So if you have node 1 receiving the increment update, it will increment state and then just pass along the increment update. So in this case, it's not submitting its entire state. It's just sending the delta in this case. So that is operation-based CRDTs. So I've talked about kind of the definition of CRDTs, but how do they actually go about guaranteeing consensus? We haven't really addressed that much. So let's dive into that a little more. So what the paper says is that CRDTs guarantee consensus through this idea, or through this concept of strong eventual consistency. So I mentioned before eventual consistency, kind of like in the Cap Theorem. So they propose essentially a new concept, which is strong eventual consistency, which I'm going to refer to as SEC, just a little shorter. So in order to understand SEC a little more, let's dive a little more into EC, eventual consistency, and define that a bit. So the paper does give us a definition of eventual consistency. It's a lot of writing, so I'm going to narrow it down a bit. So the paper says that eventual consistency means that replicas eventually reach the same final value if clients stop submitting updates. So in just kind of the base sense, if in our Google Docs example, if we have users collaborating together in one document, say their meeting is over or they're done communicating for the night, once all the users have stopped submitting updates, our system will eventually then come to consensus, because now you have all the operations flying around and they can eventually come to consensus. But the thing is, there's no guarantee of when it's going to happen. It could be immediately, could be a minute from now, could be an hour from now, a day from now. There's no guarantee of when the consensus will happen. And so the paper talks about how this is potentially an issue or like a waste of resources, because you could have an EC system where one of the nodes executes an update immediately, but then diverges from the rest of the system, or diverges from the rest of the nodes in the system. So if it diverges and there's a conflict, you have to roll back and figure out, okay, what happened? What's the true state? So an example of this is, say we have two nodes, and in this case, their state is in the form of a set. So what if I told you there's a scenario where both of these nodes could receive the same updates as one another, but still diverge? It can happen. So let's say that node 1 receives 2 add operations, so it gets to the state of A and B, and then also receives 2 remove operations from the client. So after all these 4 operations, it's back to kind of an empty state. Well, node 2 can receive these same exact updates, but still diverge. The way it can do that is if it receives them actually out of order. So if it receives the remove operation first, let's say there's like a network partition, network outage, networks are pretty finicky. So there's definitely a chance that the operations could be received out of order. So if it receives a remove operation first, the state is empty. There's nothing to remove right now, so it's just going to ignore the operation. So then if the rest of the operations come in, add A, add B, remove B, so now we've received the same operations, but our state is as conflicting. It's diverging. So there needs to be some sort of consensus now, like a rollback. Like they need to communicate with one another. Maybe Paxos or Raft, they communicate which one is the authority. But the paper says that this constitutes a waste of resources because if you need to, whenever a conflict emerges and you need to roll back and communicate with each other, you're wasting clock cycles, a lot of stuff is happening. So what it says is that, the paper says, is that CRDTs avoid this by requiring a strong condition. They don't require just eventual consistency, they require strong eventual consistency. So the definition of SEC is all replicas will have the same state if all the nodes in the system have seen the same updates. So regardless if they've received them out of order, as long as all the nodes in a system have seen the same exact updates, they'll be in consensus. So there's no idea that if they'll be in consensus as long as they've all seen the same updates. It doesn't matter if the client stops submitting updates or how long it takes. Just as long as all of them see them, they'll be in the same state. So in a strong eventual consistent system, this wouldn't happen. Or if it does happen, it won't matter because they'll still be in the same state. I know it's kind of confusing because I just talked about how this would diverge, but this is just by definition. By definition, even if two nodes receive the operations out of order, they will be in the same state. So how they achieve this, we're going to get into that. And so the paper talks about, the paper defines a new concept. It defines strong eventual consistency, and then it goes on to say that this is kind of the controversial, or like the reason why this paper became so well known is because they said CRDTs are essentially the solution to CAP. Because with CRDTs, our replicas are always available for reads and writes, so they're highly available. They can work independent of network conditions, so they have partition tolerance, and they're going to have the strongest guarantee of consistency. So while they do say this is the solution to CAP, they also admit, in kind of right here, SEC is weaker than strong consistency. So they do admit that there's still a trade-off of consistency in the system. But the reason why they were comfortable saying it's the solution to CAP is that a CRDT is essentially the closest thing you're going to get to having all three letters. You're going to have consistency, almost strong consistency, and then availability and partition tolerance. So that's kind of where this idea of CRDT as a solution to CAP came from. It's kind of like a marketing ploy to make the paper more marketable. So there's some truth to it, but if you want to believe it all the way, it's kind of up to you. So I've defined strong eventual consistency, but I'm kind of leading you around. We still haven't talked about how this actually works. So let's get into it. But the best way to learn how CRDTs actually work is to actually build a CRDT. So let's kind of dive into a bit and see if we wanted to make one right now, how we go about doing it. It's going to be a high-level thing, so don't worry, there's not going to be a lot of code, but just a high-level understanding of CRDTs. So let's say that we wanted to build a distributed set. So we wanted to have a data store that was a set. It can be distributed, so it will act as a CRDT. So just for definition's sake, our set is going to be a list of elements where each element is unique. So there's going to be no two elements in our set that are the same. And if we try to add an element to the set that already exists, the state of the set won't change. So our set is going to have three operations. You're going to have a query, you're going to have add, and you're going to have remove. So in real life, if you were building a CRDT, you would have this query operation because you need to have some sort of read operation. But for the sake of this talk, because we're focused more on how to get consensus, read operations don't affect our state in any way. So we're going to be mostly ignoring this query operation. But just for the sake of real life, if you were actually building this, you would have some sort of read operation. And so for syntax sake, I'm going to denote the set with curly braces. So the set will be everything, or all the elements in the set will be everything inside the curly braces. So, and also because we need to have our CRDTs communicate in some way, I'm choosing to use operation-based replication or operation-based communication. The reason for that is, our set can grow indefinitely. If we have a really, really popular application, our set can become really big. So if we try and submit that set across the wire, if you're using AWS, you're going to get charged a lot for bandwidth. So we're going to opt for operation-based. It's a little better in terms of scalability. So how do we actually ensure that this set that we're building is going to meet the requirements of a CRT. It's going to have that strong eventual consistency. So the paper does tell us what requirements we need. So it says that if our CRT has the semi-lattice property, it is strong eventual consistent. Like I said, I don't know much about semi-lattices, and I don't want to spend like another 20 minutes discussing them. So luckily we don't need to, because the paper also tells us what a semi-lattice is. So it says that if we're building a state-based CRT, if you want to have it to be a semi-lattice, the updates to our CRT from the clients need to be commutative, idempotent, and associative. So there's 3 requirements for a state-based CRT to achieve the semi-lattice property and also achieve strong eventual consistency. Now, in this case, we're building a operation-based. So luckily, the requirements are pretty similar, except for instead of commutative or instead of associative, for an operation-based CRT. So I think one thing I should mention, commutative replicated data types, that's another way of saying operation-based, while convergent replicated data types is another way of saying state-based. I forgot to mention that. But yeah, so that's why it says CMRDT, just operation-based. And CVRDT is state-based. So for a operation-based CRT, we still need commutativity and idempotency, but in this case, we need to have our operations have causality. So they need to be sent in the correct causal order. Now, if you don't know what these terms mean, don't worry, I'll define them. So just from this paper, or just from this section, we can kind of extract that there are 3 requirements for our CRT to achieve strong eventual consistency. The first requirement is commutativity. So a kind of definition of that is, given a set of operations, those operations will converge into the same state no matter the order of the operations. So an example of that is 1 plus 5 equals 5 plus 1. So even though we're applying the operation in different orders, it's going to be the same state. The second criteria is idempotency. So idempotency is where duplicate operations will result in the same state no matter how many times you apply them. So an example of that in math is if you have any variable x or any number x, and you multiply that by 1, you can multiply by 1 an infinite amount of times, it's always going to have the same result. So in this case, in the context of a CRDT, if it receives an add, or remove, or a query operation an infinite amount of times, the same exact operation, it will have the same state. And the last criteria is going to depend on what kind of CRT we use. Just, in this case, we're more worried about causality, but since I'm giving a talk in general about CRTs, I'll define both of them. So for associativity, in the context of our CRT, since this is state-based, whenever we submit states across the wire and a CRT receives another CRT state, they have to merge in their states together. So associativity means, in the context of CRT, is that regardless of how you group those mergings, they will have the same state. So if you have node 1, node 2, node 3, if node 1 and 2 merge their state, and the result of that then merges with node 3, it's going to equal the same state as if node 2 and node 3 merged, and then that result merged with node 1. I know it sounds similar to commutativity, like the order of operations, but it's not. This is more concerned with the grouping of operations as opposed to the order. So it's pretty similar, but there's a small difference. But that's okay, you can ignore that, because we're more worried about causality. So causality is where the operations must be received in the correct cause-effect order. So you can think about it, there are going to be some operations in our system that are a result or an effect of other operations. So it's kind of a create and remove. Removes depend on first a create, because you can't remove something that doesn't exist. So in the context of our CRT, the create operations must be received first before their counterpart removes. So this is just for a specific element. So if we're adding a 5 and then we're also removing a 5, the add 5 operation must be received first before the remove 5. Because I showed you before, if we receive elements out of order, our state can diverge. So we want to guarantee that the operations are received in the correct cause-effect order. There's issues with this, but we'll get into it. So this is kind of just a recap of the 3 requirements for consensus, or for strong eventual consistency. So back to our CRT. So we have this set they're trying to build. Does our set meet these 3 requirements? So let's check it out. So commutativity. Can our set handle out-of-order operations that aren't related to cause-effect? So let's kind of give an example. So we have two nodes. They're both starting with a set value or set state of 1, 2, and 3. So if node 1 receives a add 4 from the client, while node 2 concurrently receives a remove 2 from a different client, their state's going to change. So node 1 is going to, they're going to temporarily diverge. So node 1 has 1, 2, 3, 4. Node 2 has 1 and 3. Now they're going to pass along these operations to each other. So then node 1 has to remove the 2, and then node 2 has to add a 4. But as you can see at the end, we will have the same state. So luckily, sets by definition are commutative, because out-of-order operations aren't really an issue. So we got commutativity. Now, how about idempotency? So if we have two nodes, kind of the same example, two nodes, state of 1, 2, and 3. If they both receive remove operations from two different clients, they're both going to remove their local state first, and then pass along that operation and tell each other to also remove the 2 again. But luckily, since only 1, 2 exists, we can't remove a 2 twice. So we also get idempotency. So by definition, our set will have commutativity and idempotency. Now, what about causality? Well, I showed this previous example where if you receive out-of-order operations, our set will diverge. So just by definition, our set cannot handle causality. That doesn't mean that we can't do something about that. So in order to get causality, we have to use some extra tools that we have available to us. So we have things such as Lamport clocks and version vectors that we can use to help us get causality. Now, this is definitely going to be the most complicated. There's been some complicated parts, but this is going to be the most complicated part of this talk. So I'm going to try and define Lamport clocks and version vectors quickly, but they are a research topic of their own, so I'll try and do my best. So for the context of our CRDTs, the Lamport clock itself is going to be kind of a dictionary where you have the key, or a key value store, where you have the key is the node ID. So every node, every CRDT node in our system is going to have some sort of ID. So the node ID is going to be the key, while the value is going to be some sort of timestamp. Now, we're not going to be using Unix code timestamps, like the second since 1970 or something like that. We're not going to use that just because time can be really finicky. So instead, what we're just going to use is what is known as a logical timestamp, so it's just a counter. And so this timestamp is recording the timestamp of the last operation it has received, the last client operation it's received. So the last update it has received from the clients. So what happens is whenever a node receives an update from a client, like a new change to the system, it's going to update its timestamp. So it's going to increment the counter. So if this node receives an add operation from our user, it's going to update our timestamp to 1. And then say it receives a remove right after that, it's going to keep incrementing. So every new change to the system increments our timestamp. And so it records it's going to keep track of the last operation, last update it's seen. So what this does is essentially it's creating a history of operations, because now we know that this remove operation happened after the add operation, because if we append the timestamp to it, it's going to say timestamp of 2, where the add operation had a timestamp of 1. So we know that 2 came after 1, so there we go, we know that the remove operation came after the add operation. So that's what our Lamport clock is going to do. Now the version vectors are essentially just a list of Lamport clocks. So our version vector is going to keep track of all the Lamport clocks of all the nodes in our system, and then each node will have its own copy of the version vector. So what this allows us to do is it allows us to know if an operation that we're receiving is, like, if we've already seen the operation or if it's a new operation. Because if node A receives an update from the client, so let's say it receives an add operation, it's going to increment its own timestamp to 1, because it's the first operation it's seen, and then it's going to pass along the operation to node B. Node B can then check the timestamp of the operations to see node ID A, and then count 1. It can check that and compare it to its own version vector. So in its own version vector, see the highlighted square, it says that the count is 0. So it hasn't seen that first operation from node A yet. So it knows that this is a new operation and it should include it. So it's going to update its own state with a new operation and then update its version vector. And so now that we're adding in timestamps and version vectors, the syntax of our state is going to change a little bit. So it used to be just a curly braces with values before. Now we're going to be appending the Lamport timestamps to each value of our set. So it's going to look something like this. I tried to use like nice syntax to show it, but each element in our set is going to consist of the element value. So the element before, so before it was 10, now it's just 10 with the Lamport timestamp. So in this case, the 10 was first received by node A, and it was the first update it had seen. And then the 11 was from node B, and it was also the first update. Now this is a lot of definitions, so let's bring it together now. So why do Lamport clocks and version vectors actually help us guarantee causality? So this is I know I've been talking for a while. This is the last diagram, I promise, and after this, it's going to be almost over. So if we have a system with 3 nodes, and you can see on node A and node B, they have their Lamport timestamp. So this is a brand new system, so each timestamp is going to start at 0. And then we have the global state, just kind of top right. And then for node C in this case is going to be kind of our victim. So we don't really care so much about its timestamp or its version, and so we're not including its timestamp in the version vector. But I'm showing the version vector kind of for this diagram. But in real life, node C's diagram, node C's version vector would also include its own timestamp. So let's say that our system goes live. Node A receives the first client update, and so it receives an add operation. So our state updates, and it's getting an add operation from the client. So now it creates the operation. It's going to send it to the other nodes in our system. And it's appending the Lamport timestamp to the operation. Now let's say that node B is the closest node to node A, just distance-wise. So it's going to receive our operation first. And let's say that node B, the user at node B, didn't like that operation. So it's going to immediately remove that 5. And so now our global state is back to just empty. But now what we have is 2 operations racing to node C. Now, maybe due to like network error, slow network, maybe the remove operation gets there first. So now what are we going to do? What is node C going to do? Because I showed before that if it actually tries to implement this remove operation, it's going to diverge. Well, what it can do is once it receives this remove operation, it's going to check its timestamp, compare it to its version vector, just to see if this remove operation is new. Because in distributed systems, you can always receive duplicate operations. We want to make sure that this is a new update that we want to actually apply. So in this case it is, because it's the timestamp, the version vector of node C hasn't seen any operations yet. It's still at 0. So this counter of 1 is new, so it wants to apply that. But we know that remove operations depend first on the add operation. So we want to know, like, have we seen this element that it's trying to remove? So as I mentioned before, this 5 isn't just a 5 anymore. It's a 5 plus its Lamport timestamp. So what it's going to do is it's going to compare the Lamport timestamp of the the 5 operation, or the 5 element that it's trying to remove, and check if it's seen that. And it hasn't, because it also, brand new system, 0 counters in its version vector, so this A1 it hasn't seen. So it knows it can't add in this remove operation yet because it hasn't seen the crate. So, but now we kind of have a conundrum. You know, what are we going to do with this remove operation? We can't just ignore it because we have to apply it eventually. So one thing we could do is we could just like add to a buffer or a queue and then just wait for the add operation to come in. And then once the add operation comes in, then we can just apply the remove. The problem with that is, like I said before, network can be finicky. What if we never receive this add operation? Because we know from a high level that the add operation is coming, but this node doesn't have a high-level view of the system. It doesn't know if that add operation is coming or not. Maybe the packet got lost or something. Maybe we're using UDP and the packet got lost. So we don't know that this add operation might ever come. And if that happens, then we just have this remove operation sitting in a queue for we don't know how long. But the thing is, we don't have to actually wait for the add operation to come. Because what this remove operation is telling us is that somewhere out there, is an element of 5 with a time step of A1. It exists somewhere. So you wouldn't use a CRT to be Byzantine tolerant. So we're not going to have bad actors in our distributed system. So in this case, we can trust the information that's coming from each of the nodes in our systems. So we can trust the information in this remove operation is there. So if we can trust this remove operation, we know that somewhere out there is a 5 with A1. So what we can do is we can just trust the information, apply the add operation first, and so we just update our version vector because we're going to apply the add operation of adding 5 with a times of A1, and then we're also just immediately going to remove it. Then we're just going to update the version vector for B. So essentially, this remove operation is carrying the information we need for the add, but because it's an add and remove, it's just going to cancel each other out. So we can update a version vector, but the state is going to stay the same. So now that we update a version vector, if the add operation does come in, we can just check the timestamp of the add operation. We've already seen it, so we don't need to apply it. And so we can just ignore it, and now our state is still at empty. So in this case, we have consensus. So that is kind of how using timestamps and version vectors can help us achieve causality. So with causality, now in this case, we have commutativity, idempotency, and causality. So we have strong eventual consistency, and now our set is a CRT. So that is kind of how you might go about building a CRT if you want it to be a set. Now, I've kind of talked about all the great things about CRTs in this entire talk. It's not always that way. There's definitely some drawbacks. One of them is definitely the scale. Lamport clocks and version vectors are an example that we're going to have to use more metadata. When you create a CRT, you're going to be adding metadata to it, since you're just throwing data at the problem. So that's definitely an inefficient solution. Luckily for our set, we're actually able to remove the elements in our set. For other examples of CRTs, you can't remove the operation or you can't remove the state because it affects it. So you have to use tombstones. So in other CRT examples, even if your state is empty, if it's been around for a while, you probably have a lot of tombstones. So your CRT is going to be growing a lot. So in those cases, scale is going to be an issue. Network, if you're using a state-based CRT, you're sending your entire state across the network. So like I said before, if you're using something like a set that can grow indefinitely, it's going to be a lot of network issues. And contrasting that, if you use an operation-based CRT, you're going to have to guarantee causal delivery. So if you opt for not using Lamport clocks and version vectors, basically just the hope there's never an outage, and that your operations are always going to send in order, which is not always a guarantee you can afford to have. And then lastly, just effort, sheer amount of effort. Because CRTs are a newer area of research, there's not a lot of things such as community support. There are libraries such as AutoMerge, which was made by Martin Klepton, very smart researcher and engineer. He created a library called AutoMerge, which is like a JSON-type CRT. And there's also a library in JavaScript known as YJS, and they give a variety of CRT structures they can use. So the JavaScript community actually has a lot of CRT support. But if you're using a different language, or if you're using it for if your use case does not work well with the available solutions, you're gonna have to build it yourself. So it's gonna take a little more than 20 minutes, that I showed you before. But despite those drawbacks, there definitely are CRTs in the wild that there exist, and you might be even using one right now. These are notable things that use CRTs. So React is a data store, so they have their own set solution that uses CRTs. League of Legends, if you've ever played that, they use CRTs for their messaging app. So they receive like millions of operations a day. So definitely a good example of how CRTs can scale and they can handle traffic. And then if you ever use Atom, they have a teletype, which is a collaborative editor. You can use Atom. And then most notably Redis. Redis also uses CRTs. So if you use Redis on a daily basis, you're using CRTs on a daily basis. So I think it's pretty cool. So it's definitely an example of how CRTs can solve complicated solutions. And so yeah, like I said before, I think they have a lot of potential out there that hasn't been kind of truly shown yet. So just kind of showing CRTs in a nutshell, just kind of a small recap. It's a centralized data store. It guarantees consensus through SEC. And there's 3 requirements: commutativity, idempotency, and then either associativity or causality, depending on the CRT that you use. And then any data store can be a CRT with enough effort. And so with that, that's the end of my talk. So thank you very much. Here are resources if you want to look at that. So you got papers, then you got some cool talks at the bottom. So thank you very much.
Check.
Thank you. All right, we have a question in the back. Hands up before I even start talking. All right, go for it.
So you said that these things are commutative, but they also have a causal chain. I'm not completely clear on how it's commutative if it requires ordering.
So commutative is in regards to the operations that don't require causal. So like if I'm adding a 5 and then removing a 3, those are commutative because you can apply the add 5 first or the remove 3 first. Doesn't matter. The order of those operations don't matter. It's when it comes to the cause-effect ordering. So if like node C concurrently received the add 5 and the remove 5 at once. So that's where it's an issue because those aren't commutative. If you do the remove 5 first, you're going to get it's going to be a different state than if you did the add 5 first. Does that make sense?
So just so I understand,
Yeah.
what you're saying is that if it's commutative, you don't have to worry about it, but if it's not commutative, then you have to do some extra operations to resolve it?
Not quite. I'm saying, so it has to be commutative for operations that don't require a causal delivery. So like, so like if it's two add operations, for example, two add operations, those need to be commutative. So, what's a good way of saying this? Can you repeat the question one more time so I can get a good.
We can
drawing.
Resolve this after Q&A.
Yeah.
All right. Oh, we have another question here. Wait for the mic coming from behind.
Could you go back to like 2 or 3 slides before the thumbs down in the triangle example? So like right before this one, we resolved this example by when the B eventually wound up at node C. Node C said, oh, well, this came from an add, and the add was associated with node ID A.
Yeah.
And then, given that could assume that, then it could resolve the discrepancy. But where did that information about node ID A actually come from?
Yeah,
How did node C know that?
It kind of comes from here. So when I said that the syntax of our set has kind of changed, so now whenever we have this, so now instead of just having 10, it's going to be 10 with the timestamp. So the reason why I didn't include it, so it says add 5. In reality, it's add 5 and the timestamp. So whenever we add whenever our CRT receives an add operation from another, and it says add 5, or adding 10 example, it's adding 10, but it's also including the timestamp. So everything in green is now an element of our set. It's not just the number anymore. We're including the timestamp. That make sense?
I think so. So when a remove comes from the client,
yes.
When node B got that remove, it said remove 5. But when B forwarded on to C, it said remove the 5 that came from node A.
Yes.
All of that was packaged up by node B. The whole
so
history.
In this case, so this 5 right here, I just put 5 because it was too big to include everything. But this 5 in reality is 5 with a timestamp. So it's saying remove this 5 that has a timestamp of A1. So when it says remove 5, it's not really just remove 5, it's remove 5 A1.
Okay.
Does that make sense?
Yes.
Okay.
Right up front here, and then we'll work our way over that way.
Hi, thank you. It's a really interesting talk. I'm not sure if, it sounds to me like consensus and consistency are the same thing, and if they're not, what's the difference?
Yeah, it's a good point. So I think consistency is, there's a variety, so I guess with the Cap Theorem, you can have a variety of consistencies. There's actually, oh man, I didn't include, there's a good graphic on that. So you have strong consistency, where it's kind of like SQL, where you have transactions. So our state won't update until all the nodes in our system first apply that change. So in that case, if we had strong consistency, whenever, like for Google Docs example, whenever I were to press 5 or an A key in my Google Docs, if it was strong consistent, the document wouldn't update until first my CRT applied the change, and then also send out the changes to all the other CRTs and receive a confirmation back that they had all applied the same change.
So it's fully synchronous in that case, is one way to think about it.
So I guess consensus is this state where it's consensus is where everything is consistent. Consistency, I guess, when it comes to the Cap theorem, you have different levels of consistency, but by definition, if your system is consistent, like if in this moment, if you take a snapshot of your system, and everything's consistent, it's also consensus. It's also in consensus. Does that make sense? Yeah, but like when it comes to consistency, there's varying levels of how consistent your system can be.
You were next, and we'll work our way over that way.
Hi, I like the talk. I used to work on Google Docs, so it's good.
Awesome.
So my question is, the consensus problem, as classically stated, is one where all the readers agree on the value. And in this world, everyone disagrees on the value. So how is this consensus?
What do you mean by they disagree on the value?
Well, everyone has a different view. They have a divergent view, which eventually converges.
Yeah. So that's why that's why it's not really the solution to CAP. So in this case, with eventual consistency, you have the nodes diverge, but they will eventually become consistent, but there's no guarantee of when the consistency will happen. With strong consistency, same thing happens, they can diverge, but there is a guarantee of when the consistency will be, is that when all the nodes receive the same updates, they'll be in consensus. So you can still temporarily diverge. So if I submit an update to my local node, it will apply the local update first. So it's diverging in that moment, but then once it's broadcasted out the new state or the new operations to everybody else, and they've all received them too, then they'll be consistent.
Do you know when you're in consensus?
The definition the paper gives is that you'll be in consensus when all the nodes, like not time-based, like I don't know how long it's going to take, but there's more of a guarantee. Like if your updates only take 10 milliseconds to get to each other, then you can say, then maybe you can create even an SLA that in less than 100 milliseconds, your state will be in consensus, if you know that's kind of how your system operates. It's going to be dependent on the system. There's not like a time guarantee of when it's going to happen. It's that when all the nodes in your system receive the same set of updates, they'll be in consensus.
It implies that there's no partitions. Like all the partitions are healed, and then all writes have stopped. It will get to the consensus point, right? Yeah. So it implies a number of things about the network that may not be ever true in certain cases, I think, as well.
Because I guess the way that it's just kind of contrasting it to eventual consistency. So with eventual consistency, there's no guarantee whatsoever. Not even if all their nodes receive the same updates. Because they can diverge in that case, you might have to do some sort of rollback. With strong eventual consistency, they will diverge. You don't know when they'll necessarily, when time-based, that could be an hour from now too, but you know that as long as all the updates do occur, there's not going to be any need for a rollback, because as long as the nodes have received the updates, they'll be in consensus. Make sense? Okay.
I think both of you had, so we'll get you and then you.
So if you go back to the same question, the same slide where you got the 5, remove 5, the reason why we get consistency at the end is because both these transactions cancel each other. So you can ignore the add 5 that comes later on. But what if there are transactions that don't cancel out each other, like an update, for example?
What do you mean?
So if the first transaction you get is increment a number, and the second one you get is increment it again.
So yeah, if you were building a counter, that's the thing with CRDTs is there's not kind of one size fits all. If we were to build a counter, it would require different things. So you'd also need to probably add a Lamport timestamp or not a timestamp, but you probably need to give it an identifier. So if you do an increment add operation of add 1, you might give it some identifier, some UUID, that this is an add 1 with this ID of this, so that makes it more unique.
Yeah, you're losing idempotency if you're just doing increments, and it breaks the model.
Hi, I really enjoyed the talk, first of all. I think my question is kind of piggybacking off of the answer to the last one. So basically, it seems like we happen to use version vectors and Lamport clocks in this specific case of a set here in order to satisfy the requirements to build a set like this. I'm wondering, are there like other tips and tricks that you might use for other kinds of data structures, or are you just kind of applying this same or similar combination over and over again to different kinds of things?
Yeah, it might depend on like the type of data structure you use. So for example, me and my friends, we built like a collaborative editor similar to Google Docs, but we use CRDTs instead of OT. And so in that case, it's a set, but it's more of an ordered set because you are like the characters had to be in a certain order. So it's kind of an ordered set. So in that case, we did use version vectors and Lamport timestamps as well as you had to essentially create your own sorting system because you couldn't depend, like we used arrays for data structures, but you can't depend on the absolute indexes of arrays because those will shift depending on how many elements you have. So you have to kind of create your own ordering system in that case. So yeah, it depends on how complex you want your CRT to be. If it's just a Boolean flag, for example, like if you just wanted to have like a feature flag, like if you want to know if this event happens, then we have a consistent system. So like you might start with just false, and then if one node receives the update that's looking for, it might flip it to true. In that case, true will always win. So like your consistency protocol will depend on your use case.
Yeah, I think it goes back to the concept of CRDTs are not necessarily a drop-in replacement. You have to build on top of the concept what data structure you need and what structures you need on top of that. Like using a set, you can then build a bunch of other types of data structures as well. So.
I think I'm beginning to build the intuition that this is more of a definition than a tool necessarily that you can go plug into a code base. This is just saying if you want your thing to work, you might try making it an SCC, and here are the things you need to ensure in order for it to be an SCC. So when we say things like, it needs to have causal delivery, what we really mean is if you can ensure causal delivery, then you'll have a much easier time than if you're on a network that doesn't have causal delivery, you're going to have trouble making it an SCC.
That's why I mentioned REST before, because REST is kind of how we choose to design our API endpoints. Like REST isn't a strict thing. It says, you will have a better time if you use REST. So like gets don't change your state. You have posts and so REST is kind of a concept that we choose to adopt. How closely you adopt is up to you.
And building on the question over here about things, operations that don't commute, and this example, if the things that we're racing, instead of being add 5 and remove 5, were that node A had received add 5 from the client and B had received add 5 from the client, then does that fit here, or does that break this and you have to go put another fiddle on top?
So that's actually a good question. I was kind of expecting someone to ask that. So in that case, we will have to do something about that because node B, if it receives an add 5 from the client, the 5 in its system will have a times of B1. Whereas node A, if it receives an add 5 from the client, its state will have a 5 of A1. So in that case, if you receive 2 add 5s, you essentially add the timestamps together. So in that case, it'd be a 5 with a times of A1, B1. That make sense? Because in that case, you want to have, the whole point of CRT is that the state will be deterministic. So the reason why CRTs don't need to talk to each other to know what the state is because the updates will always converge into something that is deterministic. So if you have, if your B receives a 5 and your A receives a 5, their timestamps are going to be conflicting because one's A1, one's B1. So in order to resolve that, when each of those receive the other operation, so node A is going to receive the add 5 with B1, the 5 won't change, but you're going to be adding its timestamp to the timestamp that already exists. So you're making one cohesive state. Because then the B will do the same thing. It's going to add the A1 to its timestamp. So in the end, you're going to have 5 with A1 and then also a B1. Does that make sense?
And that's why Lamport clocks are their own talk?
Yeah, that's why Lamport clocks are definitely complicated.
I think we got time for one more, and there are like 4 hands. Okay, great. In the white and black shirt, I think you had one first before everybody. So,
Okay, so the Lamport timestamps, are they actually part of the paper, or are they just a technique that you're using to help meet the prerequisites of the paper?
They definitely do mention timestamps by name. So they do say, like, they do address, like everything I'm kind of mentioning here is roughly on the paper. So the paper does mention that causal delivery is an issue for a lot of things, because you can't always guarantee in that. So if you can't guarantee that your operations will always get sent in order, you can use timestamps and versions to essentially create a history. So that way that you can depend on the history to know how to converge things.
But maybe in theory, if you have some domain-specific knowledge that lets you avoid Lamport timestamps, if you have some other way of like meeting those requirements, then you can do away with that specific.
Yeah.
Okay.
Because the overall guarantee is you need to have causal delivery. So how you achieve that is up to you. Yeah.
All right. On that note, we'll go ahead and we can continue this conversation afterwards at the bar. It's Broome Street Bar. Like I said, it's Broome Street and West Broadway. I also have one other bit of errata. I got the date wrong for the next talk in my opening. It's the 17th, not the 11th. I was given bad information. So blame the other guy. All right, that's it. Thank you so much.